Thanks. I'm Paul Bruffett with Devon Energy, a big data and advanced analytics architect. A little bit about Devon Energy. So we're a $22 billion company, but not a whole lot of folks have heard of us because we're upstream oil and gas. And so we're an independent oil and gas producer based in Oklahoma City. We're focused on onshore US and Canada. We're primarily an unconventional producer, which means that we produce from tight oil formations, tight natural gas formations. So we do a lot of horizontal drilling and hydraulic fracturing in order to produce, which means the wells are very technical for us to develop. They're very technically challenging, demanding. We don't just kind of stick a straw in the ground and start producing, right? So some of our wells are about 2 miles long horizontally, and the pay zone that we try to stay in is as small as 30 feet there, almost 2 miles away from where you're drilling. So it's very technically demanding, and at the same time, our industry is under tremendous pressure to be cost efficient. So the question is kind of, how can we ramp up activity while maintaining technical excellence? And so what I'm going to talk about are a couple of different use cases that we've implemented in Databricks, some of which use graph data processing, which I'll talk about more at the end. And so kind of the key thing for us is how do we use a combination of the cloud, big data, analytics, and automation to dramatically improve efficiency and to help the company scale. Because at the downturn, we were as low as two drilling rigs. Now we're up to over 20. And so how do we kind of keep up that pace of activity without kind of growing our headcount like we did in the past that proved unsustainable, right? And so we've implemented a number of solutions that honestly we tried before using big data, using Azure and Databricks that just didn't work. So one of them is mapping all the historical production in the continental US. And actually, this is one of my favorite use cases, so I'm going to talk about it really briefly. But we drilled a well, and it didn't produce nearly as much as we expected. We actually got negative pressure when the reservoirs engineers figured we'd get positive pressure, which is what you want. And it turned out we'd produced more than we expected historically. And so there's this massive data set that goes all the way back to the 1800s that shows how much oil and gas has been produced from each formation basically by month for forever, right? And so we developed this composite map that used all of that data and produces a heat map that shows how much production by formation by sort of a gridded area across the entire continental United States. Obviously, that's really hard to do using another solution, so we implemented that using Spark and are actually moving that to the cloud and to Databricks. We implemented that on our old Hadoop system. Predicting problems with well completions. If we pump too much sand in there, we can occlude the wellbore and have to drill it out. So we built a real-time solution that streams data through Kafka. We train on a number of platforms, including Spark. It kind of depends on which has given us the best results. And then we, in real time, score completions jobs while the fracking crews are out in the field, and we basically say, what's the likelihood a screen out will result? Another one, we're analyzing invoices and well reports to extract entities and basically line items to automatically process them. So the training on this is obviously the really hard part, right? Taking all of our millions of invoices, PDFs, and doing extraction and processing, basically cracking them and processing them. Predicting subsurface attributes is one that I'll talk about a little bit more a little later. And then migrating our data warehouse and ETL infrastructure. And so we use Informatica and SAP HANA. We're trying to take some of those workloads that aren't as well suited for those solutions and move them to the cloud-native platform. So this is a little bit about our platform as we see it. I'm not going to drill into each of these, but the key capability areas are what we call the data reservoir, which is our data lake, and it's more of a logical construct because we need object-based storage. We also need relational data store and reverse index/search, which is Elasticsearch, and we use Cosmos DB, which is an Azure service. So by the way, we're an Azure customer. Azure is our primary cloud. It's actually our only cloud vendor, and so we have a number of solutions in there like Cosmos DB that we use. I'll talk about a little more. We have different processing, so Databricks is our distributed processing. We use GPUs, a number of other things. We let people get in here and do their own data processing, which I'll talk about more. They develop models and solutions, data solutions. They publish them, and then they can make those repeatable as data transformation pipelines. We have IAC infrastructure as code and CI/CD stuff over there, and then data movement. So one of the use cases I'm going to talk about a little bit is our attempt to kind of reduce total cost of ownership and risk in the cloud. So we built a solution to, it was basically a massive parallel processing subsurface analytics platform. So we wanted to take this data, like drilling data, like completions data, and do some analysis on how are the fracs doing as far as like frac resonance analysis. Where's the drill bit in the subsurface, because the stratas actually change around the sort of the wellbore in ways that are not always predictable from the surface, and things like that. And so honestly, we didn't know how successful we'd be with some of these use cases when we started it, and we wanted to build a prototype. So we built that prototype in about 6 months with one specific use case for drilling data at an expense of about 150 grand for Azure Cloud spend, right? But on-premise, it would have taken about $1 million for us to stand it up because we needed a massive cluster because this is a massive compute problem. And about 6 months just to procure, rack, and stack the stuff, right? And so for us, honestly, I don't think we would have gotten that, right? We wouldn't have gotten that $1 million just to prove out if it worked or not. So we built it cloud native. If the prototype failed, we didn't have any long-term contracts, right? And so if it hadn't worked, we could have just turned off the spend and stopped using the services. The other side of this, too, that I'm going to talk about is we've had on-premise Hadoop for probably 5 years now, and we're moving all of our infrastructure to Azure. So in about 12 months, we won't have a data center anymore. We'll all be entirely in Azure for all of our technology platforms. And so we've had an on-premise Hadoop cluster for about 5 years, but we never really got the adoption that we planned on, right? So we started loading all this data, we populated our data lake, and people never really came. And it was because we didn't keep our Hadoop version current, because we have all these plugins. We use SAS, we use Informatica, we use Datamir. And in order to upgrade the version of our Hadoop distribution, we had to upgrade these other things, and then they had their own dependencies. And so it became kind of this web of things that we couldn't manage effectively. And it was also really difficult for our admins to sort of maintain the yarn allocations, right? To say, well, this is how much this group should get. And some of the solutions require hard commits, like Impala, where you just have to commit a certain amount, right? And it doesn't share resources the same way. And so it resulted in us being very reticent to give people access, especially our data scientists, ironically, access to the cluster to build things because we were afraid that they'd tank our other workloads that were, production and required high availability. And so in practice, it meant we made it hard for people to access and use the cluster. We had people in there, but they never really liked it as much as they expected, right? And so we had a data lake, but we kind of didn't get that adoption. We didn't really transform the business in the way that we expected. And in Azure on Databricks, we actually now have literally thousands of tables that replicate in there on different frequencies, depending on the business requirements. And we give everybody that asks for it access. And in the future, actually, as soon as groups are sort of more widely available in the product, we'll just give everybody access, everybody in the company. So right now we have about 250 people that have access out of a company of 3,100. And as soon as we can do groups, we're just going to put everybody in there so that they can log in and get it. And the power of that is we actually had our interns start, and folks started kind of picking and choosing the databases that they needed to solve their data use cases, because most of them are doing data science use cases. And usually that literally takes weeks because they have to talk to different admins and get access to databases and get access to actual application on their desktop, right, and do their joins and queries. And now in Databricks, we just add any tables that are missing and give them access to Databricks, and it's kind of one and done. And so from a user experience, that's been, I want to say transformative, because it's really changed the way that these folks get access to data. And honestly, people have been amazed by the data that we have at Devan that they didn't realize we had until they logged into Databricks and they see a table from, OSI PySoft or something, and they realize we have a huge amount of drilling and completions data, right, for a really long history that they can do bulk queries on. And I'll talk a little bit about how we're starting to store that and manage that. So that has resulted in expanded adoption, right? And so our consumption has kind of gone linearly up of the cloud data services, which has been great because we've been delivering business value at the same time. But a really big thing for us is kind of adding new use cases to this solution, right? And so we're saying, hey, we're expanding our adoption of big data by reinventing our data warehouse. And the data warehouse reinvention's critical for us because today, if we want to add new objects, so we have a data warehouse, like I said, on HANA, and we wrap it with custom OData endpoints because that allows us a lot of flexibility to sort of abstract our data from our customers. In order to onboard a new object, it'll take us up to 6 months of actual IT development time. That's not really meeting the business requirements. And so we've started moving people over to Databricks to do that data processing and publication, and it's dramatically reduced our cycle time. And we're developing new analytic capabilities. So actually, one of our big challenges has been one of the things that the keynotes say that they're hopefully fixing, which is integrating things like PyTorch and TensorFlow with sort of our deep learning pipelines, and that's kind of been a challenge that sounds like it's getting dramatically better. So anyway, we're rewriting HANA and Informatica jobs to Spark. So we have some really large multi-billion row tables that took a long time to prep and transform in Informatica or in HANA that we've rewritten and take probably 10 minutes depending on the Spark cluster now. We're expanding our adoption of ML and AI. So one of the real challenges that we had in the past with ML and AI adoption was that our folks were getting in there and they had to try to get a bunch of libraries installed in their machines, and it made it not very repeatable. And if they went in the cloud, they needed their own GPU instance, so it made us very reticent to give that to them because it's just burning, $600, $700 a month for one user that may or may not be doing stuff that can be replicated. And so now we just give them Databricks GPU clusters, capturing and analyzing data that was previously not feasible. So actually we have a much smaller version of the Apple use case in that we're capturing several terabytes of security data a day and putting in a Delta table. So that was an interesting sort of validation of our use case. But that previously really wasn't worth it. Our security team kind of didn't have the money to put that data in HANA, and delivering self-service analytics to the company. So there are two real use cases I'm going to talk about there that have been interesting for us. And so the self-service data analytics, we have a number of engineers, technicians, technologists that understand the data better than anybody in IT. And really at the end of the day, they just want access to the data, and they want access to approved tools, and they want us to kind of get out of the way. And so to that end, we have a reservoir technologist, is what we call it, who is trying to basically understand the probability with which we would produce too much water in a specific area. And so whenever you drill a well, you produce oil, you produce natural gas liquids, and you produce water. And the quantities of each of those depends on the formation. And so in some formations, you produce an extremely large amount of water. In some, you produce very little, and you produce a lot of natural gas. And so we choose formations based on the asset mix that we want it to produce. And in this one, it produces a good bit of water that we have to haul away, right, and then process, because it's not water you can just sort of have people drink. It's got heavy metals and a bunch of salt. And so he basically wanted to say, based on our rig schedule, based on when we figure on drilling these wells, when will we overwhelm our water hauling capacity, right, and with what probability? And so in the past, he would have had to ask IT, and they were actually doing this in Excel, and it literally took them 1 to 2 days to iterate on this analysis. He rewrote it with a little bit of help from us, from my team, in Databricks. Now he runs that simulation in about 10 minutes, and the business users just key in the dates for when they'll bring wells online. It automatically goes out and it runs his analysis to say, there's a 10% chance that we'll overwhelm our water hauling capacity, right? And so that was really powerful because he automated his own workload without having to get money or time from IT, and he did it on Databricks where the data was already available, right? And so that was one of our really powerful sort of citizen-developed use cases. Another example, so here's kind of where we start talking about some of our graph adoption is, it's really lowered the barrier for entry for us adopting new technologies, kind of moving into the cloud. And so we built a number of use cases, including expanding adoption of graph data structures for analytics, heterogeneous application hosting platforms, and faster adoption of new libraries and frameworks. And so that top one, we actually tried to do some graph analysis initially, and basically we wanted to do large scale. We had a graph that we were generating programmatically that basically was a probability distribution. And we wanted to traverse that and basically find an optimal, or a number of optimal routes through it. And we initially basically said, hey, let's try this custom and use Redis for a really fast caching layer to Spark, and write a Lua script that automatically goes, and it basically does an atomic upsert on each of the nodes as it traverses the graph. And so we said, all right, well, let's try that. We don't actually have Redis in-house now because we're not a content company. And so we went out to Azure, used it as a PaaS service. We found out it was a suboptimal solution, and we basically turned it back off, and we had about a 2-month end-to-end, right? Turn it on one day, build the whole thing out, find out we want to go a different way, and turn it off. And so it's been really easy for us to kind of adopt these new technologies in a way that really we wouldn't have in the past. In the past, if we had tried that solution, we would have been stuck with it because we would have spent the money and we would have been loath to sort of turn it off and move to another approach. The heterogeneous application hosting platforms sort of speaks to some of the model deployment we heard about today. So in Azure, we do use the machine learning deployment solution that they have, where it deploys basically a model as a Kubernetes cluster, provides you a Swagger document, and gives you one user interface to sort of manage all those models, those endpoints, and their API keys. But we deploy on a number of other platforms, including Azure Service Fabric, Azure Container Services, basically just depending on the use case. That was really difficult for us to do. And then we have new libraries and frameworks that people want all the time. And so TensorFlow is really big. Now PyTorch is really big for us. So people have kind of gotten, our data scientists are really asking for that library and framework to be widely supported in the platform, and we're delivering that. It's really difficult to scale PyTorch at this time, at least for us. TensorFlow seems to have much better adoption. There's no sort of PyTorch horovod, at least not to my knowledge. If you guys know it, then I'd be glad to hear it. But we're already delivering that in the platform. And so a little bit about how we use graph analytics at Devan. So we use graph data structures to represent a number of different objects. And some of these we're experimenting with, and some of them we actually have very mature solutions with. And so we represent it for field equipment, driving routes, and subsurface analytics. And so Spark and GraphX allow us to scale our graph processing. And so we actually do most of our development in Python. Almost all of our folks like to use Python, and to the extent that they can and need to, they use PySpark. And that makes them rather successful, right? They'll sort of prototype or write things in Python, and then we'll help them move them to PySpark when they need to scale. But to be honest, we run both of those workloads in Databricks. And so not everything that we write in Databricks is actually in any kind of Spark backend. We'll just use Python, and we'll install the libraries on a Databricks cluster and let them use it there. Because what we found was a lot of our analysts and data scientists really did not care if they checked in their code. And we tried to get them to do that, and they really didn't see any point, because they said, my machine's backed up, what do I need from you, right? But then they don't really understand that whenever somebody decides to leave the company, we lose access to that code base unless if we go and troll their network drive. But that person that quit doesn't really care. And so there's difficult to create those incentives for them. In Databricks, we obviously get it all there with version history, and we can connect it to GitHub and all that, right? And so that's made it much easier for us to kind of help them scale their analytics and get them out of their desktop, honestly, whether they use Spark or not, right? Anyway, so we use Spark, and we do a lot of the sort of the data preparation transformation, and we have our experts help people parallelize it, either in PySpark, predominantly PySpark, like I said, because of its affinity with Python. But then in a lot of cases, we've actually had to sort of do heterogeneous solutions, and so we'll implement sort of the logic or the data preparation, the data transformation side of it in PySpark, and then we'll use the Scala GraphX to do the sort of graph analytics. And the reason for that is, so we use graph frames some, and I think I'll talk about it a little bit later, but it just doesn't have the robustness, right, of GraphX. GraphX is a much more mature, and since everything in graph frames is implemented on top of GraphX, basically anything you can do in GraphX, you only have a subset of that available in graph frames. And so we'll end up actually generally persisting or caching that data and moving them between the two. One that's been really interesting for us is the field equipment hierarchies. So we're starting to model those as graphs in order to model the interdependencies. And what's been kind of interesting for us at Devan is folks generally think of graphs as either I'm going to do geospatial work, right? I'm going to do route optimization, right? Or they think of it as I'm going to do social networks. But what we've found is we can significantly optimize queries by making graphs that are basically these heterogeneous sets of data that have just generic relationships. And so what I mean by that is we'll say, we've got all this different kind of field equipment, right? We've got rod pumps, we've got tank batteries, and we've got compressors, and we've got pipelines. And some of them are they're associated by virtue of their proximity, right? Or by virtue of a pipeline connecting them, or there are a number of different ways we can kind of connect these objects. We can even connect wells like that. So one well will have multiple well bores where we drill, and then we go one direction, and then we go another direction, and we go another, and it's called sort of fishbone drilling. We do that quite a bit in Canada to access multiple formations effectively. And so we actually even have a hierarchy within wells that we can model this way. But what it ends up looking like is sort of this sparse graph where we have nodes that have information about them, and because each of those different entities have different properties, we actually end up with this really wide sort of table, and graphs are just really represented in Spark as two sets of RDDs, right? A node's RDD and an edge's RDD, and you union those two to actually create the graph data structure. And so what we end up doing is we union all these different types of entities, and we really just coalesce the table into an increasingly wide sort of RDD or data frame for both the nodes and the edges. And then we can kind of convert that, and then we can look at all the interdependencies. And functionally what it looks like is you would have done that query, and you would have just done multiple joins on that table itself, right, to just sort of navigate or traverse that table. And it's massively inefficient. I mean, that's literally the point of graph data structures, right, is to help you avoid that sort of joining logic where you just continually sort of recursively join a table on itself in order to navigate or traverse it. And so by converting it, we've made these queries several orders of magnitude more efficient, which has been tremendous. The other one that's interesting for us that's kind of unique is lease operators. So historically we've said, well, this is a 3-day well where a lease operator will go to it 3 days a week, and this is a 2-day well. They're going to go out there 2 days a week. And these folks, lease operators, are the guys that actually drive to wells. These folks they'd have the same route, and they'd run the same route every Tuesday, or they'd run the same route every Wednesday, right? Regardless of how marginal that well had become. And so we're saying, well, if a well's offline that produces 10 times more than another well that just went offline, we obviously want to go to that higher producing well. So what we want to do is dynamically change the way that these folks do their routes, which is obviously a problem that a lot of people have. Our unique spin on it is most of these driving routes are actually dirt roads that don't show up in Google Maps. You don't have a map out there to the middle of some North Texas oil field where you don't have any cell service. And so we are actually having to do a lot of the work for optimizing these routes ourselves being Devon, not necessarily my team. We're working extensively with our geospatial information systems team to kind of start prototyping these solutions and see how we can continue to improve it. Because historically, it's really difficult to sort of make these composite maps where we're tracking those, and because these routes change frequently, not just the routes, but the actual paths out to the well pads, right? And then finally, the graphs can represent subsurface conditions. And so what we find is we can sort of build graphs that look at the multidimensional space of the subsurface and basically analyze either what the fractures look like for a completions job based on sort of different probabilities that we've assigned to the graph, or to drilling routes or things like that. And so we've found that we can kind of use algorithms that we're applying to graphs in order to sort of optimize or to sort of find the optimal fit, I guess you could say. All right, so graph persistence. So this is one of the things that's interesting about Azure. And so we work with Cosmos DB a fair bit. And Cosmos DB is the Azure service, kind of like DynamoDB on AWS, right? So it's a NoSQL data store, very similar to Mongo. The interesting thing about Cosmos is now we can do multi-geographic reads where we basically can say, Cosmos, I want you to deploy into a number of different Azure regions. And we can write to one of those and read from any of them. Now you can also actually do multi-master writes, and so we could write to multiple regions, and we can basically use a slider in Cosmos that governs the consistency model, and the more strongly consistent you make Cosmos, the slower it gets. And so it kind of gives us a trade-off slider, right, where we're fine with eventual consistency, but we want a tremendous amount of speed or not. Cosmos also comes with a number of APIs, which is what's relevant for us. And so it comes with a Mongo API, a Gremlin's Graph API, and then it comes with a SQL API. And actually, some of these are interchangeable. So I believe the Mongo and the Gremlin, you can actually write via Mongo and extract via Gremlin as long as you keep a certain contract in the data. And so what we find is we can actually use Databricks to create the graphs using graph frames and GraphX, and we can persist those to geo-replicated Cosmos DB instances with the Gremlin API. And then we can actually query that back out directly using custom apps on top of the Gremlin Cosmos API. So we can insert data directly into Cosmos and read it in as Databricks tables using the Databricks jars that make it work natively with Cosmos. And we're not caching it or anything like that. So basically, we're getting the real-time data back out of Cosmos in the same way that we're writing it, right? We're not, kind of persisting it out to Parquet or anything like that to make it work as an intermediary. And so that's been pretty powerful for us. Like I said, made it available as tables in Databricks. And so we actually make it available as relational tables. Obviously, the slight kind of pivot here is as we persist out the data from Databricks, it wants to persist as two different RDDs natively, or two different data frames natively. And so sometimes we actually really just do that in Parquet, and we sort of rehydrate it in Databricks without worrying about sort of the Gremlin API. So it depends on the use case. But yeah, so the power is that we can query and manipulate that from other tools while maintaining one version of the truth. The other interesting use case that we've actually started putting in Cosmos is we can tell Cosmos to do upserts itself. And so we're writing IoT data directly to Cosmos using NiFi and upserting it in Cosmos and then reading that back out into Databricks. We've actually used Delta to do some of that as well. So we're writing data and upserting it in Delta to sort of merge new changes. Because unlike most IoT data, our IoT data can actually be restated historically for up to 48 hours because sometimes the drilling rig, it ends up that we get inaccurate readings that later sort of get reassessed and restated. And so we have to sort of upsert that as we merge it in. Oh yeah, so I think I talked about this a little bit already, but the general purpose graph. So we frequently think about graphs as social or geographic data. We've used them to improve query performance by modeling relations between different entities by avoiding basically table joins. Domain-specific language for looking data out of a graph frames was actually pretty easy. So the sort of A, edge, B, and then we can add additional predicates onto the end of that is fairly intuitive after people spend about an hour or two with it if they're already pretty developmentally inclined. And so we haven't had a tremendous problem with sort of adoption on that, especially since we can integrate that with Spark and basically just produce new data frames out of the graph domain-specific language and sort of query that source data set a little more efficiently than we otherwise could. All right, so I think now's my time for questions. So thank you.
Yes, first question. Here we go.
Thank you. You mentioned at the end that you're persisting your GraphX data into Cosmos and then allowing other systems to query that, but then you're also inserting data into Cosmos.
We're also what into the Cosmos?
Inserting data?
Yes, yes.
So I'm just wondering, how do you maintain, and you also mentioned that the single source of truth is really important, that you want to have it in both places, sort of consistent. So how do you maintain that consistency across multiple graph systems?
Well, so at the end of the day, almost all the, so Cosmos, it doesn't obviously do any locking across, right? It's not like an ACID database, it's basically a modified MongoDB. And so at the end of the day, almost all of our writes become upserts. And so we say every one of these pieces of data that's going to get written is going to get upserted. And so we really haven't had any kind of collisions. Because we have a fairly strict consistency guarantee that we've enforced on Cosmos. And so even if we have two different jobs that are both making modifications, we really have never had the case where two different writers were modifying the same document. We also really haven't had the issue where we get out of order data and try to upsert it differently, if that makes sense, because we've added the timestamp onto our pre-processing. So I guess what I mean is we've never gotten an old record that we've tried to upsert on top of a newer record and had that collision, because we take care of that basically before the fact using something like NiFi, where we have custom NiFi flows that do a lot of the data preparation, transformation, and error checking before we write them back. Honestly, a lot of our bulk analytics doesn't sort of go onto that raw data store either. We kind of make sort of enriched. It's a little bit like that. We get all the streaming changes in, we get them into Cosmos, and then we sort of have enriched Cosmos downstream, if that makes sense, where we've done like business unit specific subsets or whatever the case is, user specific subsets. But at the end of the day, Cosmos takes care of almost all of it for us using upserts. And we just do sane upserts, I guess I would say. I hope that answered your question.
Time for a couple more questions. Here you go.
Thank you for the presentation. I had a question. You were deflating back into Cosmos and then deflating back into Databricks. I'm not clear why the round trip, so if you could have just saved it as an RDD, so if you could elaborate a little bit on that.
Yeah, so it depends a little bit on the use case. And so in some cases, in a lot of cases, what we're really trying to do, so in Cosmos, we have these other custom applications that can sit directly on top of it, right? And so our application development team has built solutions that use Cosmos as the back end, and they don't have to go through Databricks for that. And so we can make much faster sort of random reads and writes from Cosmos than we could do from another data store, and we can do it very, well, I mean, there are other data stores that can do fast atomic reads and writes, but Cosmos allows us to do that basically functionally infinitely scalably at a very low price point. And so we can do a lot of the data enrichment and then basically put it in the serving layer that we pay a fairly nominal fee for, and then allow other applications to come in and do transactional reads and writes on top of that data store in a way that if we had persisted it in Parquet and served it out of Hive or Impala or any of those solutions, it'd be really difficult, right? So we get a different sort of performance profile for custom applications. It's all about custom applications that are going to like people's mobile apps or things like that. But if we were just looking to read and write it from Spark to Spark, yeah, we don't really do that. We do Parquet if we have to do persistence or something, or Delta, something like that.
Additional questions?
Dennis, CPAM system. Question about your ingestion. So you mentioned that you have lots of devices drilling, and you building kind of graph that describe relationship between the parts. And The question is, how do you basically relate this relation between those devices? It's kind of manual process, or you kind of, yeah.
Yeah. So I mean, at the end of the day, we have to have the foreign keys. I mean, we don't have any sort of like fuzzy intelligence to basically say, hey, these two things are related in this way. We have to have we have to have actually defined relations, right? Like there's a pipeline connecting these two or things like that. The nature of the connection depends on, obviously, the nature of the entities, where a rod pump would be connected to a compressor in a different way that a compressor would be connected to, maybe a tank battery. In that a pipe would very directly connect those two things, but a rod pump would be sort of an indirect relationship. And so we sort of have to mine the data set that we have and build it on an entity-specific nature. But obviously, to the extent we've connected two entities that have downstream entities, right, you can navigate that hierarchy even if we haven't directly connected, which is literally the point, right? So I hope that answered your question. I think I'm out of time.
Any additional questions? Nope, in the back.
Thank you. How do you store the geographic data? Do you consider only points or also lines and polygons?
Yeah, so it depends on the data. So to the extent that it's a specific entity that we have a lat long for, it usually just goes in an RDBMS or possibly a NoSQL data store. But we have a lot of data that's actually more like domain-specific, like shape files. We have a lot of different shape files. We work extensively with Azure, so we use a lot of Azure software, which is the geospatial. Like I said, we have an entire GIS team because we care very much about, like, well, what projection is it in, right? Because there are multiple projection formats depending on the place on the Earth. And so there's a lot of nuance, which is where we would use more like a shape file or even a specific, like application-specific format. And so usually we try to do more open format like shapefiles because we can actually read those in using the Azure library to Spark, which is very nice, and we can do our own plotting and things like that. But it's usually one of the two. So.
Have you utilized any of the graph algorithms in GraphX?
Sorry, what about GraphX?
Have you utilized any of the graphic algorithms?
Yes. So we actually, we've experimented with a couple, but the one that we went the furthest down the road with was Dijkstra's. And so for us, like PageRank isn't very relevant, right? Because that's not really our deal. But we actually implemented a slightly modified version of Dijkstra's because we were interested not just in sort of the most optimum path, but a number of sort of possibly optimum but divergent paths, if that makes sense. And so we, to a large degree, we actually, we implemented it fairly vanilla, but we did it in Scala, and basically that's where I was saying we actually prepare that graph using Python, and we persist it and we load it back, not in Cosmos in that case, and we do our actual GraphX processing in Scala because we kind of have that heterogeneous team that has different skill sets. So, but predominantly Dijkstra's because that sort of route optimization or cost optimization through a graph is the most relevant for most of our use cases. Although we have done a little bit with like sort of allocation back to predecessors and things like that.
All right, well, big thank you to Paul again for the session, and we'll have a lunch break after this.